Hello everyone, here we talk about sampling distribution. Let's have a look at an example. The student score from a test result have been collected here. We can see in column A, we have total 62 scores recorded. That is our population. Now we pick up a sample with 5 scores from this population. Every score has equal chance to be chosen. In this case, the sample is called simple random sample. Here's an example showing in green area. That's one of the possible sample with 5 scores. 5 is called sample size. We can see the sample could be changed. Potentially, there are many possible samples. How many possible size 5 simple random samples can we make? We only care about picking up 5 scores from the population. Any 5 put together would be one of the possible simple random samples. There's no specific order in each sample for the scores. In that case, this is the combination situation. We can simply use Excel function combination to get the answer. Here we go. Combination, total we have 62 data in the population. We pick up 5 of them. How many possible combinations we have? Surprisingly, the answer is more than 6.47 millions. Now let's have a look at the population mean and the sample mean. We can find them easily by using Excel function average. The population data are located from A2 to A63 and the sample located C2, C. Obviously, we can see they are different. Sample mean is different from the population mean. If we choose different sample, the sample mean changes. We can also easily calculate the difference between sample mean and population mean. It is called sampling error. Sometimes the sampling error is positive, and sometimes the sampling error could be negative. Since we have so many samples, more than 6.47 millions, that means we have more than 6.47 millions sample average or sample means. They could be close to population mean. They could be far away from population mean. The sampling error could be bigger, could be small. So that is basic reality we have observed. In that case, the sample mean can be considered as a random variable. More than 6.47 million possible values for this sample mean. We are talking about what kind of probability distribution this sample mean may have. Now let's sort out the idea about sampling error in mathematical expression. Sampling error is the difference between a measure computed from a sample and the corresponding measure computed from the population. If we consider average value, then the sampling error comes from the difference between sample mean and population mean. If we consider the proportion of a special group in the population, and then this kind of proportion can also show up in any simple random sample. Correspondingly, the sampling error for proportions can be expressed as the difference of the proportion from sample and the proportion in population. From the example about student score, we showed 62 student scores are collected. From this population, we can get population mean 71.43 and the population standard deviation 16.8. We also can organize all this data into frequency distribution. Here it shows. Then we show what we did. Randomly pick up 5 scores as a sample. And then we have sample mean. The sample mean is different from the population mean. We have sampling error from this sample. The error is 1.37. The sample mean is only 1.37 points higher than the population mean. Considering that, say if we do not know the population mean, and then we use the sample mean to represent the population mean, it doesn't look too bad. Let's try again. Now we pick up another random simple sample with 5 scores. We have different sample mean. Then our sampling error showed here as negative 16.63. If we use the sample data from the second sample, if we use the sample mean from the second sample to represent the population mean, it seems really bad this time. Similarly, if we continue doing so, we see the sample mean varies and corresponding sampling error could be quite different. Thinking about 200 random sample with sample size 5, we have 200 sample means listed here. We can build frequency distribution. We can build up frequency distribution with this 200 sample means. Here it is. And with this 200 sample means, we have average value 71.25, standard deviation 7.91. And we list our population mean and the population standard deviation here, so you can see the difference. From the early observation, we can come out the following conclusions. Sampling error can be small or large, can be positive or negative. The amount of error varies. The sampling error depends on which sample is selected. The average of the sample means is approximately equal to the population mean. That's what we just observed here. When we pick up 200 possible sample means, we calculate average value from these 200 possible sample means. It seems close to population mean, 71.25 and 71.43. The variation in the sample means is obviously less than the variation of the population. The distribution of sample mean is approximately normal. Now we try some random samples with size 10. Here we have a list, 5 simple random samples. And we also can see they have different means and they have different sampling errors. If we repeat the process, we pick up 200 random samples with sample size 10. We organize them into frequency distribution again. Here we go. From these 200 simple random samples, we come out average value 71.32 and standard deviation 5.12. When we compare to the population mean and the population standard deviation, we observed similar situation about sample mean and sample errors. And we also observed the average of the sample means is approximately equal to the population mean. It seems getting closer this time. The variation in the sample means is getting less compared to the population standard deviation. And again, the sampling distribution is approximately normal. So we can come out with the idea larger sample sizes result in less variability in the distribution of sample means. And here we can have a summary. Put all the information together and we can compare them. See original population distribution roughly a little bit like normal, but for size 5 samples, the sample mean distribution pretty much like normal distribution. And again, when the size increases to 10, the sample mean distribution more towards to normal distribution. Now we summarize our observations together. Come out with theorem 1. For any population, the average value of all possible sample means calculated from all possible random samples of a given size from the population equals the population mean. It is clear. Theorem 2. For any population, the standard deviation of the possible sample means calculated from all possible random samples of size n is equal to the population standard deviation divided by the square root of the sample size. So clearly, if we know the population standard deviation for all the possible sample means with fixed size n, the average of all the sample means, and the standard deviation of all the sample means are related to the population mean and the population standard deviation. Theorem 3. If a population is normally distributed with mean, mu, and standard deviation sigma, the sampling distribution of the sample mean x bar is also normally distributed with a mean and standard deviation as below. We put 1 and 2 together. Few examples from our observations. The calculation result are showing on the right side of the screen. When the sample size is 5, when the sample size is 10, or when the sample size is 20. And we can see the trend of the sample mean standard deviation goes down, down, and down. Theorem 4. The central limit theorem. For simple random samples of n observations taken from a population with mean mu and standard deviation sigma, regardless of the population's distribution, provided the sample size is sufficiently large, the distribution of sample means x bar is approximately normal, with a mean mu x bar equals mu, and the standard deviation sigma x bar equals sigma divide square root n. The larger the sample size, the better the approximation to the normal distribution. Here are the examples. Original population distribution is shown in this chart. When original population distribution is uniform distribution, when the sample size is 2, we can see how the sampling distribution for the sample mean changes. When the sample size rises up to 5, roughly normal distribution shape has shown up. If The population distribution is like a triangle shape. It is symmetrical, and we can see the corresponding sampling distribution transforms with the size 5 or size 30. Extremely, if we have a population distributions very skewed, not even symmetrical at all, but even for sampling size 4, we come out a sampling distribution is skewed, but roughly a normal shape showed up. If sample size increases to 25, we can see a quite pretty normal shape there. Here are some notes about central limit theorem. The sample size must be sufficiently large. If the population is quite symmetric, then the sample sizes as small as 2 or 3 can provide a normally distributed sampling distribution. If the population is highly skewed or otherwise irregularly shaped, the required sample size will be larger. A conservative definition of a sufficiently large sample size, normally considered bigger than 30. Z-value for sampling distribution of sample mean is usually used to describe the event related to sampling mean to find the corresponding probabilities. The relative distance that a given sample mean is from the center can be determined by standardizing the sampling distribution. A z-value measures the number of standard deviations from the mean. Here it is. From the central limit theorem, the standardizing process for sample mean is described as z-value by using a random sample mean minus the mean of the sampling distribution, then divide by the standard deviation of the sampling distribution. Here let's work out an example. A food processing company produces French fries for fast food outlets. The distribution of French fry length is considered normal, with mean length 4 inches and standard deviation 1 inch. What is the probability of selecting a simple random sample of 100 fries with a sample mean exceeding 4.1 inches? The basic information provided from this example, we have population standard deviation 1, and we consider sample size 100, and we really get one simple random sample, which give us the mean 4 inches. That is the sample mean from this one simple random sample. And then we're looking for how much chance from all the potential possible random simple samples the sample mean would be exceeding 4.1 inches. So that is the event and corresponding probability. We express x bar greater or equal 4.1. We can use Excel function to find the answer directly by applying the proper sample mean and standard deviation from this sampling distribution. The answer is 0.1587. Alternatively, we can find the standard value first. Since the sampling distribution is normal distribution with the mean 4 and the standard deviation by using population standard deviation divided by square root sample size. So we come out the standard value for this simple random sample is 1. And then we can apply standard normal distribution function in Excel conveniently. Since we can access Excel and use Excel in a convenient way now, so it's not necessary to look for the table. We can find the answer right away from here. Similarly, what is the probability that sample mean with size 100 would be less than 3.85 inches? The event shows like the chart here, and we can apply Excel function, conveniently find the answer 0.0668. And we can also find the standard value and then use either normal distribution table or standard normal distribution function in Excel directly, and we can find the answer quickly. Now we apply this idea to a proportion in a population. For a special focus group, population proportion is the fraction of values in a population that have a specific attribute. Here it is, simple percentage by counts, how much that special group takes in the population. When we randomly pick up a sample from this population, we would be able to turn out a similar fraction based on the sample information. So the counts all come from the sample. We use a different letter, P bar, to represent sample proportion. We understand the sample proportion would be normally different from the population proportion, so the difference being described as sampling error for the proportion. If we only want to give a one number to answer the population proportion based on sample information, the best estimate of the proportion would be P bar. Any inference about how close your estimate is to the true population proportion value, that will be based on the distribution of this sample proportion P bar, which underlying distribution is binomial. If the sample size is sufficiently large enough, normally we say NP is bigger than 5 or say NP is bigger than 10. Then the normal distribution can be used as a reasonable approximation to the discrete binomial distribution. The mean and standard deviation for the normal distribution would be described as the mean would be same as the proportion from population. The standard error or standard deviation for the random variable sample proportion would be related to the population proportion. Here's an example. According to past records for a large retail chain, the proportion of customers who pay for their merchandise with a debit card is 60%. Suppose a particular store within the chain examines a sample of 100 purchases and observes 48 customers used a debit card. What is the probability of a sample proportion of 0.48 or less if the true population proportion is 60%? So we have basic information, the background assumption 60% as the population proportion, that percent of the customers, their merchandise being paid by debit card. Based on that, we can find out the average value and the standard deviation for the sampling distribution of the sample proportion. What we're looking for is, for all the potential possible samples, the sample proportion is equal or smaller than 48%. How much chance that would happen? With the normal distribution in our mind, we can apply that directly. Here shows how the event and the corresponding probability described in the chart. So we can apply Excel function directly, find out the answer. Or alternatively, we can calculate standard value for this specific sample proportion. The standard value is negative 2.45. And we can check the standard normal distribution table, or we can apply the Excel function, which is a standard normal distribution function. We can compare the original format by using general normal distribution information. They both give us the same answer. The probability for a random sample proportion to be smaller or equal 0.48 is 0.00715. Here is another example. A big problem for taxpayers has been the recent increase in fraudulent tax returns being filed with the IRS in the name of taxpayers. Suppose the IRS believes that 15% of all taxpayers will be affected in 2016. Assuming the true proportion of taxpayers who get hacked is 15%. What is the probability that more than 40 in a random sample of 200 will have had this experience? In this question, we assume the population proportion is 15%, and we have a random sample size 200. We try to look at the probability more than 40 from this random sample would have had this hacking experience. So the event being described by this bottom line proportion, 40 out of 200, give us 20%. We're looking what is the chance for any random sample. The sample proportion would be bigger than 20%. The corresponding normal distribution for this sample proportion would have the average, same as population proportion. Standard deviation by calculating this square root turn out 0.025. So here is the event on the right side little tail. We try to find the probability of that event. Put all the information in the Excel function. We can find the answer right away. Similarly, we can find the standard value first, which is 1.98, and then we look at standard normal distribution chart. The right side little tail defined as the standard value 1.98. So the area of the little tail would be the probability we are looking for. It can be found from standard normal distribution table, give us the answer 0.0239, or from standard normal distribution function, we find this answer right away. We put them together with the earlier expression by applying general normal distribution function in Excel. All the original information in this function. They all give us exactly the same answer. The probability is 0.0239.